So, those of you who don't know me, my name is Ben Sachs. The company I work for, Sachs & Associates, offers training in C and C++ for companies around the world. And I'd like to talk to you today a little bit about attributes in C++. And I'm going to be talking mostly about standard attributes for modern C++, but I'm going to start by giving you a little bit of background. And I think the story of attributes really starts before they were a standard feature of C++. Because many compilers, this has been true for almost as long as there have been compilers, don't just implement the core language features that the standard requires in C++. They also implement additional features through extensions. So, for example, the ARM compiler provides this qualifier __IRQ to make it a little easier for you as a programmer to write interrupt handlers. The GNU compiler provides this attribute path for letting you control the memory layout of structures, and this attribute cold, which allows you to declare that a function is rarely, if ever, called in the program, and that informs the optimizer that it should optimize the function for space rather than speed, because it's not going to be a significant part of your runtime. Now, attributes like this attribute cold here can affect the performance of your generated code. So they're the sort of thing that you often want to be able to take advantage of, but because they're compiler-specific extensions, that can be difficult. If you're writing code that you want to be portable, and you'd like to be able to compile the same code using multiple toolchains, using these extensions really harms that portability. When a compiler tries to parse one of these attributes and it doesn't understand it, usually the result is a compiler. So one of these extensions, I should say. So if you want to use these extensions, traditionally, what you'd have to do is you either have to say, okay, I'm just going to commit to using the GNU compiler, and then I can make use of the GNU-specific extensions. Or you would need to do something to compile those extensions in conditionally, which can be a little fragile, depending on how many targets you want to support today, how many you want to support tomorrow. You can be spending a fair bit of effort making sure that all of your conditional compilation flags work out the way you want. And so modern C++ attributes provide a way that we can help address this problem. So attributes in modern C++ look like this. They're a sequence of one or more tokens enclosed in double square brackets. So they can be a simple token like a noreturn here, which is just one token right there. Or they can be something more complicated like that deprecated attribute there that has a string literal that says don't call this. And we'll talk more about exactly what those do further on in the talk. But when the compiler sees an attribute that looks like this, any double bracketed attribute that it doesn't understand, it's required to ignore. So this provides a certain level of security that allows you to write your code more flexibly, because you can take advantage of these extensions where they exist. And if your extension is implemented using one of these modern C++ attributes, then other compilers that don't support that extension will just compile the code as if you hadn't written that attribute in the first place. And you'll still get behavior that works on the other end. It might not be quite as fast or quite as efficient as it would be on a platform that understands that extension, but you'll still get working code. Now, as the standard evolved, it became clear that this wasn't useful just for compiler extensions. There are also language features that it made sense to implement using this attribute syntax. Because there are some of the things that are in the language really fundamentally change the behavior of code.
But there are other features in the language that aren't strictly necessary to make the code do what you want. Instead, they serve to do things like help you detect error conditions, or they improve code performance. And so implementing those sorts of features as attributes has become the preferred way of doing things because they're effectively backwards compatible. As long as your compiler knows that it's supposed to ignore any double square bracketed attribute that it doesn't recognize, you can use the latest cutting edge stuff. And if your compiler doesn't yet support it, it's just ignored. If it does support it, you get the new and improved behavior. So let's take a look at some of those features. So one of the first attributes that was added in C++ 11 was this noreturn attribute, and it indicates that a function never returns. Now, I have to be a little pedantic in my terminology here, because a function with a void return type still returns in most cases. It doesn't return anything specifically, but it does use the same process of returning back to the call site to get back to where the function was called. Whereas a noreturn function really doesn't return to the call site at all. So one of the ways in which this is useful is that compilers will often issue warnings if they notice that code that you've written is unreachable. So if I fed my compiler code that looked like this, where I have something that I expected to be executed after the return statement, most compilers would flag this as unreachable code and say, I think you're doing something wrong here. Now, that works fine in this case because the compiler has an intrinsic understanding of what the return statement does, the fact that that's going to be the effective end of the function. But if I have a more opaque function there that doesn't return, the compiler might not be able to tell that without some additional help. So for example, the standard exit function from C never returns. Its job is to terminate the program with a specific exit code. And so in modern C++, we declare this as a no-return function to make it clear that this function never returns back to the call site. Once you call this function, you're not coming back. So now, if in modern C++, if I write code that looks like this, now my compiler can reasonably flag the code after the call to exit as unreachable, where it wouldn't have been able to do that if the function hadn't been declared no return, because it would have assumed that the function is at some point going to end and come back to this point. Now, one of the other reasons you might want to declare something no return is that there is a small performance benefit to it. There is some amount of code associated with returning back to the call site of the function. And so if the compiler knows that your function is never going to return, it can omit the generation of those instructions. It can leave that part of the function out. And the result is you get code that's slightly smaller and slightly faster. Now, as I said, you want to be a little cautious about doing this. So here we have a function that doesn't have an explicit return statement. It has a return type of void. All it does is print out a value to standard out. But it still returns control back to the caller, because flowing off the end of the function is the same thing as returning, effectively. So this is a function that shouldn't be declared no return, because it still gets back to the call site through the standard return mechanism. Now, one thing that no return functions can do is that they can terminate by throwing exceptions. Doesn't necessarily mean that you'll never exit the function that was declared no return. It just means that you won't exit it using the normal function call return mechanism. So here we have a function foo that always throws a standard logic error. And I can put this inside of a try block in this other function bar here. And the compiler can tell in this case that the code that comes after the call to foo inside that try block will never be called, will never be run, because it occurs directly after a no return function. And whatever that function does, it's not going to come back to the call site in the ordinary mechanism. On the other hand, the compiler does understand that it may still reach the point of that catch block where we catch the logic error and output the goodbye message. That code will be treated as reachable. Now, one of the reasons you want to be so careful about making sure that you don't declare functions as no return unless they actually don't return is that if a no return function gets to a point where it ordinarily would return, the result is it produces undefined behavior. As I said before, the compiler has the license to omit the return code from that function. And if that code isn't there, what happens? You just keep executing whatever code comes after that function in the compiled executable, and that's probably not what you wanted to do. Now, the compiler is encouraged to warn you if a no return function might actually return, but for an arbitrarily complex function, it might not be able to do that. In many cases, it will warn you, but it's not guaranteed that the compiler can catch anything, or can catch everything there. So you want to declare functions as no return if, and only if, they don't return. So moving on to another attribute, one of the common things that we see as code bases evolve is that you'll have a piece of code that you find a better way of doing the thing that that code was responsible for. And you replace it with a better version. Or rather, I should say, you'd like to replace it. But you have a lot of existing code that already uses the old interface. And so you might not want to go through a single big bang revision of changing all of your code at once. But you do want to introduce the new way of doing things, a new and improved interface, and tell people to migrate away from the old interface and towards the new one. So we see an example of this in the C++ standard. Back in C++03, we had auto pointer, which was a smart pointer type that had some surprising behaviors. And so in modern C++, we eventually got the tools to write improved smart pointer types that had less surprising behaviors, like unique pointer. And so as a result, auto pointer has fallen out of favor. It was deprecated in C++11, and in fact, now it's just straight been removed from C++17. But there was that period of 6 years in there where auto pointer lived in this sort of gray area, where it was part of the standard. It was something that you could use. It was guaranteed to be there. But we were encouraging you not to use it. There were superior alternatives like unique pointer that you should be using instead. And so it was what we call deprecated. And in modern C++, C++14 specifically, we now have a deprecated attribute that lets you tag your own code in this way. So if you tag something as deprecated, and you actually use that piece of code somewhere in your executable, the compiler should issue a warning telling you you're using something that's been deprecated, go find a better way of doing things. And you can apply this to all sorts of different stuff. So you can have deprecated variables, deprecated functions, deprecated types, type defs, aliases, all sorts of things. You can even have deprecated individual enumeration values or explicit template specializations like this. And one of the things that you can do, because just saying deprecated isn't necessarily all that helpful, as I showed you earlier, deprecated can take a string literal as an argument. And that string literal is intended to provide information about why the thing is deprecated or what you might want to use instead. So here, for example, I have a function print that I've declared deprecated because I have a new function write that I would prefer that people use instead. I don't want to completely get rid of the print function from my code just yet. But I don't want new uses of that print function to enter the code. I want people to be using the write function instead. And on many compilers, this attribute, that string literal that's specified there, will just be directly in the error message. It'll just say something like, here's the message from the GNU compiler, and it actually includes prefer write in the result. So another situation that attributes can be helpful in is when writing switch statements. So often when we write switch statements, the cases within the switch are independent of each other. And we make sure that that's the case by including a break statement at the end of every case. And because if we forget to include a break statement somewhere, then control just falls through to the next case and continues executing there. And often that's not what we want. So here, for example, I have some code for a TCP connection state machine for a server. So somewhere inside that server code, I have this switch statement that looks at the state of the connection. And it has a case where it says, if I've just received the first part of a connection request, go ahead and send back the appropriate response to continue establishing that connection, and then break out of the switch. If I've just received the first part of a close a connection request, go ahead and send back the appropriate response and then break out of the switch. If I forgot to include one of those break statements, I would fall into a different case here. For example, if I missed at the first break in this case, I'd never be able to no one would ever be able to connect to this server, because I would first send out a response that said, okay, I'm willing to continue connecting. Oh, and then I immediately send the terminate connection message. So people wouldn't really be able to connect, and that would be not a very good server. So some compilers will warn you in situations where you forget to include a break statement when fall through would occur. And so that can be very helpful in catching errors. But sometimes you actually do want to fall through to the next case in a switch statement. So here's more code from that same switch statement. And I have a default case here where suppose that my TCP server has gotten into an unusual connection state, and I want to somehow recover from that. What I do in that situation is I reset the connection to put the connection back into a known state, basically terminate it, and then I go back into the listen state at that point, and I pick up as if I had been in the listen state to begin with. I just start waiting for a connection from some client. In this case, I actually want the fall through to occur, because the appropriate way of handling a default state is to reset the connection and then continue on into the listen state. If I got a compiler warning about fall through here, that would be annoying and distracting, because I actually want the fall through to occur. And in C++17, we can now make that clear to the compiler with the fall through attribute. I can place fall through at the end of a case in a switch statement. And that makes it clear to the compiler that I really do want to fall through to the next case, and it shouldn't warn me about that situation. And fall through can even be executed conditionally like this. So in this case, I've augmented the code so that we'll only reset the connection if we've been in an unknown state for a certain amount of time, if we've reached a timeout. So if the timeout has been reached, we reset the connection and fall through into the listen case. Otherwise, we just break out and go back and let the server go back to doing whatever it was doing before, and then we'll check back on the connection state at some point in the future, and maybe we'll have timed out then. Now, the next statement to be executed after a fall through has to be a case label. So I can't just put a fall through at the top of a case like this, where the next statement is actually an if statement rather than a case label. In this case, the compiler will flag that fall through attribute as invalid, because the next statement isn't the sort of thing that I can fall through into. And this also applies if I try and put a fall through at the very end of the last case, because in that situation, Again, there's nothing to fall through into from the final case. So that's not a valid place for the fall through attribute. Yeah, do you want to use the microphone to...
Sure. The semicolon is needed to have a statement?
Is the semicolon necessary, is the question. So I believe the semicolon is necessary. When I've seen it used, I've always seen a semicolon there. But I have to admit, that's something I didn't test when I was running through the code for this particular talk. So I'll check that at some point. Okay. Any more questions? I'm about to move on from the fall through attribute. So if there are any more questions about that, feel free to ask. Okay. So another situation in which compilers often warn us is when we have unused variables. Many compilers, if I feed it code that looks like this, where I have a function called half that has a local variable y that I just give the value 10, but then I don't use y anywhere in the body of the function after that point, most compilers will warn me about this situation. They will say, wait a minute, you created this variable, but you never used this. Did you mean to do something else? And in general, this is a good thing, because it helps us catch programming mistakes. It helps remind us that maybe I intended to have another line in this function somewhere. But occasionally, compilers will warn you about these things when you don't want them to. And I think the most common case where this comes up is when you're using the assert macro. So here we have a function foo that takes two parameters, I and j. But the purpose of j as a parameter here is only to check a precondition of the function. We use an assert statement to verify that I is less than some value j. And then we continue on to use I. And the rest of my foo function here doesn't use j at all. The only purpose of j was to verify that precondition. And because I'm using assert in this situation, j is actually only used when I compile in debug mode. Because when I compile in release mode, assert statements are compiled out. So I'm in the annoying situation where I have code that looks perfectly fine when I'm writing it, but then I submit it and compile it for release, and I get an unexpected warning, because now all of a sudden j isn't actually used in this function. So C++17 provides an attribute for dealing with these sorts of situations, the maybe unused attribute. And it lets the compiler know that it's possible that a particular value won't be used during its lifetime, and that's okay. You as the programmer intended that. You don't need to be reminded via warnings or other messages that this thing isn't being used. Now, unused variables are what we typically think of when we think of getting warnings about unused entities, but you can actually put maybe unused in lots of different places. So you can have not just maybe unused variables, but maybe unused functions or parameters or types, type defs, etc. So while we don't see compilers right now issuing very many warnings about these things, one of the nice things about having attributes like this is that it's not necessarily helpful for silencing warnings so much right now, but it allows compilers to be a little bit more aggressive about giving us warnings about these things being unused. That right now they might be reluctant to issue, because now we have this maybe unused mechanism that provides a way of turning those warnings off if we don't want to see them on a case-by-case basis. Here are just a few more examples of where you can use the maybe unused attribute. Now, one of the things that a lot of these attributes deal with warnings and similar behaviors. And in general, the standard doesn't like to be too prescriptive about what sorts of error messages a compiler needs to produce. It will tell you when a program is ill-formed, But in terms of warnings, the standard doesn't like to be too prescriptive in those cases. So maybe unused, strictly according to the standard, is actually a request, not a command. The compiler does have the license to ignore you and say, yeah, I know you said maybe unused, but I'm going to issue I really think you need to know that this thing is unused, and I'm going to tell you anyway. Now, I haven't found any situations in which a compiler actually does this, but because the standard doesn't want to be overly prescriptive with warning messages, it's, from a strict standpoint, you think of this as a request. So was there a question?
Yeah, just a quick question. Can you go back to the previous slide?
You want me to go back to the previous slide? This?
Yeah, where you had like struct and using. How come sometimes it's nested in the middle of the statement and sometimes it's left?
Oh, here? The placement rules for attributes are, there are many different places in which you can put these things. They're fairly intricate, okay. And I didn't want to spend a lot of time discussing them. So this is where I'm using the placement of attributes for the purposes of this talk in what seems to be the general consensus about where to place them, but it's more flexible than I'm letting on in terms of exactly where these attributes have to be placed.
Okay, thank you.
Okay, so another situation where this is actually sort of the reverse case. Sometimes we have functions that have return values that aren't very interesting. There are standard functions like memset that behave this way. Memset returns a copy of its first argument. Did you know that? I suspect a lot of people never think about the return value of memset because it's not a particularly useful thing. You had to already have a copy of that argument in order to pass it in. So it's very common for people to ignore the return value of a function like memset. But of course, there are other functions where you really don't want to ignore the return value. So here, for example, I have a function createWidget that returns a dynamically allocated widget object. If I call the createWidget function and I don't look at the return value or pick it up and do something with it, then the result of that is I have a memory leak because I've allocated something with new and there's no corresponding delete statement for it. But so it would be nice if the compiler could warn me in this sort of situation. But because some functions have return values that are often ignored, the compiler doesn't really know which return values are interesting and which return values aren't, unless we tell it. And now we have a way to do that in C++17 with the noDiscard attribute. And this is the one that I think you're probably going to use the most out of all the attributes I'm going to mention here. I think this one, it's not that common that you create a function that doesn't return, but there are lots of times when you create functions where the return value really should be used for something. It would be very surprising to you as the author of this function if no one picked up the return value and did anything with it. So if I declare my createWidget function noDiscard, then the compiler should give me a warning if I don't actually use the return value for anything. If I just drop it on the floor, I should get some sort of warning from the compiler. So you can think of this in some respects as the opposite of maybe unused. The point of maybe unused was to silence a compiler warning where you knew you wanted to ignore something and you needed to tell the compiler that. For noDiscard, the point is, I didn't mean to ignore this thing and I want you to specifically prompt me to make sure that I use it if I forget to do so. So it's not surprising, perhaps, that in the same way, maybe unused is thought of as a request, not a command. The compiler does its the best job it can to try and figure out if you're not using the return value of a noDiscard function. But it's possible it might not catch everything. So It's not 100% ironclad, but it can certainly be helpful in terms of preventing these sorts of mistakes. Now, another place that you'll commonly see this used is you have functions that use their return values to indicate error conditions. There are lots of standard C functions that return EOF on failure. So because these functions often succeed, we're used to them succeeding most of the time, it's easy for us to forget to check for EOF and not actually write the code to handle the failure case. And if these functions were declared no discard, we would get that prompt from the compiler that would force us to think a little bit more about that error condition. So this is another place that no discard can be helpful. And one of the ways that you can make that a little bit easier is that you can, in addition to no discard functions, you can have no discard types. So when you declare a class or enumeration type, you can declare it with the no discard attribute. And what that does is, any function that returns a type that was declared as a no discard type is implicitly a no discard function. So here I have an enumeration error code that lists out a number of different return values from a function, a number of different behaviors that the function could have had. I declare that no discard, and then I don't need to place no discard on functions that return error codes because they're all implicitly no discard because it's on the type. So this can reduce some of that clutter a little bit. So another attribute, here we're getting into the attributes from C++20. So some of these are things that you might not necessarily have access to just yet, but one of the things that's nice about attributes is if the compiler doesn't understand a double bracketed attribute, it's required to ignore it. So there's not that much harm in using it, even if your compiler doesn't understand it. So when you write code that includes a branch, an if statement, a while loop, things like that, usually it's not a 50-50 split which branch is going to be taken. Often, one branch is more likely than another branch. So here, for example, I have a function factorial that calculates factorial values recursively. And most of the time, when I call this function, it's probably going to be called on a value larger than 1. So in many cases, I'm going to fall down into the recursion case. I'm not going to go into the terminate case of just returning 1 when I get down to factorial of 1. So if the compiler knew that it was more likely to fall into the else case rather than taking the first if case here, it might be able to generate more efficient code. And in C++20, we have a way of giving it that hint with the likely attribute. So we can attach likely to an else case like this. And that tells the compiler that it's free to make the assumption that that is the most likely situation from the most likely outcome from this if statement, and it can optimize accordingly. And unsurprisingly, just like there's a likely attribute, there's an unlikely attribute that lets you tell the compiler that a particular branch is less likely than others to be taken. So if you have more than 2 cases here, in this case, I just have an if and an else. And so the effect of saying likely on one versus unlikely on the other is likely to be the same thing. But if I have several different branches, then I might want to tag some of them as likely, some of them as unlikely, and it can be a more complex situation. Yes?
Case statements?
Case statements? Normally, the way that I think of a compiler as executing a switch case statement is with a jump table. So I wouldn't normally think of that as something where I'd expect to get much benefit out of the likely attribute.
Well, that presumes that you have this monotonic
That's
set of cases.
That's true, yes. everywhere I've seen likely and unlikely used so far, it's on a more traditional, an if statement or something like that. But it might be something that you can also use on a case statement. I'd have to go back and check on that. Yeah.
Can I do it inside complex Boolean conditionals to affect which way the short circuitings predict?
Inside of a complex Boolean conditional. What? So the question was, can I include these attributes somewhere in the middle of a conditional and have that affect short circuit logic? I don't believe so. Maybe I'm misunderstanding what you're picturing here, but the short circuit evaluation is just the if condition will have the same result one way or the other.
If A or B, but A is unlikely and B is likely.
If A or B, and B, I haven't seen it used that way.
It's guaranteed to
I don't-
relate left to right, so likely and
It's,
likely will not
it's
count.
just the branch predictor. I'm saying A is unlikely and B is likely. All the ordinary short circuiting still occurs.
I can't. I don't believe it can be used in that context, but I'll check on that. That's an interesting suggestion. Yes? Where does it go in a ternary statement? I believe. Let's see. In the case of the ternary, I want to say that it goes, if you wanted the question mark branch to be the likely scenario, I believe it goes after the question mark, but I need to double check on that. Now, one thing, before you get too enthusiastic about this, one thing that I should say here is that these attributes are designed to be used sparingly. You shouldn't take this as advice to go off and just every time you write an if condition, put likely on something or unlikely on another branch. This should be something that you do in response to information from a profiler or when you have other information that would suggest that you really want to give the compiler this hint in this case. If you just, the standard draft actually goes so far as to say that excessive usage of either of these attributes is liable to result in performance degradation. So it is possible if you misuse these, that it could be what we sometimes call a pessimization rather than an optimization. It could make your code slower rather than faster. So you want to be a little judicious in your use of likely and unlikely. So the next example involves, I think it comes up most commonly when you're doing situations like policy-based design. So I think most people who are familiar with this came to it through Andrei Alexandrescu's book, Modern C++ Design, which actually predates modern C++, but that sort of thing happens sometimes with titles. And the idea behind policy-based design is that you want to write one conceptual class type that has a set of behaviors that you can choose between at compile time. So rather than having to write several different versions of a class that differ only in terms of how they allocate memory, for example, you can write one class template that uses an allocation policy, like I'm showing here. And then by supplying different allocation policies at compile time, you get the performance as if you had written several different classes, but you only have the maintenance cost of actually having to maintain that one class template. So in this case, I'm using two different policies with my class foo here. I have an allocation policy for determining how it allocates memory, and I have a comparison policy for indicating how foo objects should be compared to each other. And I'm including them as data members in my class foo. If you've read Andre's book, you'll know that he does things a little bit differently, and I'll explain why in just a moment. But for now, let's just take a look at this picture here, where we have the two policies as data members. Now, they might have state information associated with them, but then again, they might not. It's not uncommon for these policies not to have any data. So for example, here's an allocation policy that just uses the standard new and delete. It doesn't need to track any state in order to handle these allocations. So my allocator just has member functions, no data members. And this is not an uncommon thing to see with policy classes. The same thing can be true of my comparison policy. Here, I have a policy that just compares two values using the less than operator. It doesn't need any state to make these sorts of comparisons. There are other policies that I could have used that might have state. And then having these things as data members in this case would be important. But in this particular case, I'm using policies that don't have data members. But the thing is that class objects in C++ have to have a size of at least 1. Even if a class has no data members, it occupies at least 1 byte of storage. That's just the nature of how C++ works. And so the result of that is, using these policies as data members, I can wind up with a bigger class than I would expect to have, because each one of those policies has to be at least size 1. So in this case, foo has to have at least 2 from alloc and comp, plus whatever additional storage it would have for its other data members. And this can be, a meaningful percentage of the total size of the foo object. It can make my code slower and less efficient. So one way that we could solve this problem would be to inherit from the policy types rather than making them data members. It turns out that base class subobjects are somewhat special in C++. Every class object has to have a size of at least 1. And that's true even of base class subobjects. But if you derive from a base class that has no data members, that doesn't necessarily increase the size of the derived class object. What you can think about is, so in this situation here, where I have two policy classes, alloc policy and comp policy, if neither one has any data members, they both have to be at least size 1. But the standard allows for the possibility that that 1 byte that they're required to have is shared. They both occupy the same storage. So the result of deriving in this case, rather than using composition, is that my foo object could be smaller. So this might provide benefits in terms of reducing the size. On the other hand, I might not want to derive from these things. It's possible that these policies aren't really designed to be used as base classes, depending on how I've structured my type. In this case, the two policy classes that I showed you, they don't have virtual destructors or any other virtual functions like we would normally expect from classes that we would use as base classes. So it's not clear that deriving really gives me the behavior I want in this case. So in C++20, we'll have another way of doing this, which is of creating subobjects with an effective size of 0. And it's this no unique address attribute. So in this case, I could go back to using my allocation and comparison policies as data members and declare them with no unique address. And they would be allowed to share that space in the same way that they would have been allowed to if they were base class subobjects. So this allows us to avoid creating unwanted inheritance relationships in this situation. The no unique address attribute has to be applied to non-static data members. It doesn't work for static data members, and it doesn't work for things that aren't members of classes to begin with. I should say class types. And when the C++ standard says class types, it really means classes and structs and unions. Now, there's actually another use of no unique address for the situation where you might want to declare something no unique address even if it actually does have data members inside it. So suppose I have this type little here that consists of an integer and a character, and I'm compiling my code on a typical 32-bit platform. What I think I would expect to see on most 32-bit platforms for this struct is that the memory layout would look something like that table there. So first we would have 4 bytes for the integer, then we would have 1 byte for the character, and then there would be 3 padding bytes at the end of the struct to give it so that it's properly aligned. So we'd have a total size of 8 for our little object. And now suppose I use that little object as a data member inside another type, big. So big has 2 data members, a little, and an array of 3 characters called ID. I think the memory layout on that same 32-bit platform would typically look like this, where you have, again, 4 bytes for the integer from little, 1 byte for the character from little, and then 3 padding bytes in the little object. And then the 3 bytes for the characters in the ID member, and 1 more padding byte at the end of the big object, for a total size of 12. If I declare my little object as no unique address inside the big object, that has the effect of telling the compiler that it's allowed to reuse the padding bytes inside the little object for the purpose of storing other data from the big object. So by declaring little to be no unique address, I think in many cases what you would see is that that would reduce the size of my big object down to 8. Because now I would have 4 bytes for the integer, 1 byte for the character from little, and then instead of having 3 padding bytes at the end of little, that storage would be reused to store the 3 characters in the ID member of big. So this can help save space in another way. Similar behavior. Yes?
If you were to do a memset on your little member, would that then overwrite the other member as well?
Yes. You're saying if you did a memset and you used size of little, for example, sorry, to repeat the question, the question was, if I do a memset on the little part of a big object, what happens? And what happens is, yes, it would potentially overwrite data outside of the little object, assuming you're using size of little as the length of the memset, because that little object, well, it's right there in the name. It doesn't have a unique address. If you overwrite that memory, you could also be overwriting something else. I think there was another question here. Are you allowed to take the address of L?
In order to feed the memset, for example. In order to feed the memset, for example.
Could you even feed the address of L to memset?
Yes.
I believe you can, yes. The thing is that, the tricky part about it is that the size of little is the size of the little member inside of a big, in some sense, is different from size of little when it's a standalone type. That's where it kind of becomes a little murky.
So size of L would be smaller than size of little?
No.
No, if you actually take size of L, you'll get the size of a little object. The question was, does size of L get affected by this? And no, it doesn't. Yes?
Do you have an example that works with something that could be a misaligned type?
Well, I was just about to say, yes, that the question was, how does this affect alignment? And the answer is it doesn't. What I showed you in this example worked well because characters have a size of 1 and an alignment of 1. So it was easy for the character data to reuse the padding from another structure because it has very loose alignment requirements. If the other data members in big had more strict alignment requirements, then they still have to be aligned properly. So even if there might be padding that could theoretically store an object, if that object has a stricter alignment requirement, the compiler won't necessarily choose to use that padding. The other restriction is that if you have two data members of the same type, they can't overlap, even if they're declared no unique address.
Even if they're empty?
Even if they're empty. I believe the way to think about it is that you go back to, suppose I have an array of objects that contain no data members. If the objects were allowed to have a size of 0, what would it mean to plus a pointer on that array? Add 0 to the size of the thing? You wouldn't be able to step through it. And so I believe that the same behavior is what underlies the fact that two objects of the same type, even if they're both declared no unique address, can't really share space. Yes?
How does that work with the car at the end of little and the 3 cars that we added in ID?
How does it? I'm not. The question was, how does that interfere with the previous example?
Yes.
I'm not sure I'm following what your concern is there.
So the compiler sees the type of little as little. It doesn't take the underlying type into account of the last car of which the padding is against. Because here it's saying that these two types cannot overlap because they're the same type.
Right.
If each of them was a 1-byte car.
Oh, I think I see what you're saying. You're saying that back here, yes, I was using characters in, the last thing in little was a character, and the first thing after that in big was a character. Mm-hmm. And is that a problem? And no, it's not, because it thinks of them in terms of it's thinking about it in terms of the structure type little, not the things that go inside a little.
Got it. Thank you.
Yes. Okay. So in this situation, even though I have two objects declared no unique address that have no storage, I would wind up having a struct that was at least size 2, because the two allocators each need their own phantom storage. So far I've been talking about the standard attributes, but I also want to touch a little bit on the non-standard attributes. I mentioned before that one of the reasons that this was introduced into the standard was so that compilers would have a way of using this syntax to implement extensions that could be used without reducing portability. But they don't, in order to make sure that whatever attributes a particular compiler implements as extensions don't interfere with future name choices for possible standard attributes. Compilers are supposed to place their compiler-specific attributes into attribute namespaces. So the GNU attribute cold that I showed you earlier, if you want to use that as a modern C++ double square bracketed attribute, it looks like this, GNU : code, or cold. So, one complication on this. I've been telling you that compilers will ignore attributes that they don't recognize. And that's true. They won't let it affect the generated code, but they might warn you about it. And this is a double-edged sword. It's a blessing and a curse. Because if I misspell deprecated as deprecated here, it's nice that the compiler can tell me you spelled something wrong. I don't recognize the attribute that you were trying to use in this case. So give me a warning in that situation. But it's annoying that well-formed attributes that the compiler doesn't understand could still elicit warnings because the compiler doesn't support them, specifically extension stuff like this. So how can you solve this problem? Because we generally don't like to ignore warnings. You could disable the warnings. Unfortunately, a lot of compilers use one warning code for all unrecognized attributes. So that's a little bit, so you kind of have to use a blanket approach to that in some situations. And you wouldn't be able to detect misspelled attributes. Now, you might be able to make it work by compiling it so that the warning is only disabled in certain build modes. So for example, in debug mode, you could enable the warning, and you would see warnings about attributes in the code that you're currently working on. But then when you go to submit your code and compile for release, then you wouldn't see all of these warnings crop up in the generated code. That would be one approach. I think a more common approach is, what you often see people do is they wrap up attributes in macros that look like this. So they test to see whether the compiler supports a particular attribute. And then they create attributes, or they create macros that translate to those attributes if the compiler actually supports them, and if the compiler doesn't support them, they translate into nothing. They just go away. So in this situation here, I've created a macro deprecated message that uses the form of deprecated with a string literal, and then I can use the deprecated message macro instead of the actual deprecated attribute. Now that's kind of annoying for conditional compilation, but one of the things that makes it easier is that the standard includes feature test macros for these things. So you don't need to do very much work to get the conditional compilation to be pretty darn accurate in this situation, because the standard mandates that the compiler provide these feature test macro definitions that you can use for preprocessor if statements. So you can check to see, does the compiler support C++ attributes at all? That's the CPP attributes in the first position. And then there's has CPP attribute and the name of a specific attribute that you want to know whether it supports. And then you can use that to define these conditional macros. In theory, you can also test for other non-standard attributes in this same way. The compiler encourages vendors to make this feature test macro work for their own compiler-specific attributes. But since it's not standard, your mileage may vary. Now that has CP, one thing I wanted to mention here was that you do actually need to test for both of these in my experience. You might think that, well, if it has the no discard attribute, do I need to test for CPP attributes at all? And my experience is that some compilers will actually define has CPP attribute, no discard will be true, even when C++ CPP attributes is false if you're compiling in like C++ 03 mode. Go figure. The value of the attribute is actually sometimes interesting. It's the time that the most recent revision to the standard was made that the compiler supports. So for example, in C++20, no discard is getting a string literal parameter the same way that deprecated had a string literal parameter. So you'll be able to explain why you don't want to discard this thing. And so in this situation, you could use the value of the has CPP attribute no discard to test to see, does your compiler support that specific version of no discard, and implement a macro for that. So closing out, prefer the double bracketed attributes over compiler-specific syntax for extensions. Declare functions as no return if and only if they never return. Use deprecated to mark code that shouldn't be used. Mark fall throughs with fall through. Unused entities with maybe unused. And use no discard to avoid ignoring return values that shouldn't be ignored. And that brings me to the end.